just fine on Monday, but okay, it works. Great. So yesterday you have learned about the basics of GPU programming, about directive-based models that allow you to, with some annotations, offload your existing code to the GPU with minimal annotations, and about non-portable kernel-based models, which are closer to the metal and specifically require you to outline the function that is offloaded to the GPU, so-called kernel, and to manually allocate and probably move the data, although there are unified memory models that approaches that copy the data automatically, just like, for example, swapping works when offloading unused RAM pages to the hard disk. And today we'll go to portable kernel-based models, which are similar to how the non-portable models work. So they're quite close to hardware and usually require you to deliberately outline what part of the code is offloaded to the GPU. But unlike, say, CUDA or heap, they are not limited to a single vendor. Now, technically, heap is also not limited to a single vendor. You can use heap to target NVIDIA devices. But while it is possible, I think it's very niche use case. So usually, people only use heap for AMD devices. And among those portable models that we'll discuss today will be C++ standard parallelism, OpenCL, and SYCL. There is also Kokkos, but I will skip it for today. If you're really interested, you can read this document. It has some basic introductions. Follow yourself. So, as the name cross-platform suggests, it's about using the same code to run on multiple different devices without having to rewrite it for every single architecture. You don't have to rewrite your code, have separate code base for NVIDIA, AMD, Intel, and CPU, for example. But you can just like write a single code and run it anywhere. And unlike, say, OpenMP, usually you have somewhat more control over how things are executed. So you have the benefits of kernel-based models in that you have quite tight control over the hardware, and the benefits of directive-based models that they are rather portable and not limited to a single vendor. And of course, some frameworks claim that, all portable models claim that they are not limited to GPUs. They can work on CPUs, FPGAs, and whatever new accelerator is out there. Well, it is somewhat true, as in it does technically work, but these are close to hardware. There's kernel-based models. You deliberately write the code how it is run on the device. And while GPUs from, say, NVIDIA and AMD have quite distinct architectures, and you need to think about those details if you're really optimizing your code, they are quite close to each other if you compare them with CPUs or FPGAs or various AI accelerators. So while you can use the same framework and literally run the same kernel on totally different architectures, on CPUs, FPGAs, GPUs, it is usually not the best idea, because you likely want to restructure your algorithm. You don't just, while the code can run, it's unlikely that the same algorithm can run efficiently. It's not just about using different framework, it's about most likely heavily rethinking the whole approach to how you parallelize your code. Again, if we are going past basic for loops and vector addition, there it's usually quite trivial. in matrix multiplication, that already is quite a rabbit hole of how best to lay it out, as you have learned yesterday with, for example, shared memory, which is a feature of GPUs not necessarily present on other hardware. It is a common feature among all the major GPUs out there, but for other types of accelerators, that's not the case. And obviously, people wanted to use single framework to target different hardware for as long as different hardware existed. Sorry, somebody is saying something? Or is just noise?
No, it's just noise. Can continue.
Okay, good. Yeah, so people wanted to avoid duplicating the code and write code once and run anywhere. And that was the case for more or less most of the high-level language for CPUs, but for GPUs, every vendor was pushing their own frameworks, CUDA being the most notable example, and in many cases, it is the killer feature of NVIDIA hardware, NVIDIA ecosystem, just the sheer amount of software and libraries and their quality is implemented there. But yeah, when you write your own code, you probably don't want to rewrite it everywhere, and especially nowadays, as if you look at top 500, for example, in the top 5 machines there, top 5 biggest supercomputers, at least among those that care to submit the ratings, we have NVIDIA GPUs, AMD GPUs, Intel GPUs, and CPU-only systems. So really, it is very varied out there, and people are getting interested in such portable frameworks. And besides OpenCL, SYCL, and standard parallelism that we'll talk today, there are other approaches, other solutions like Alpaca, Kokkos, also present here, Raja, as well as, directive-based models. They're portable, and to a certain extent, all the special GPU languages like Chapel or Futhark, those are also claimed to be portable because it is a separate language. But within this language, you're not limited to any particular vendor. And for this course, and in practice, all these models happen to be based on C++. So if you're using Fortran, you either have to get some kind of C interface and call C functions, or you have to use, say, directive-based models there, because it just happens that all these programming models are C or C++ based. So let's start with C++ standard parallelism, because it is the simplest one, and probably one would say even closer to the directive-based models, because it allows you to do minimal modifications to your code. So in practice, standard parallelism is just like what it says. There is standard library, STL, that is part of the C++ language, and since C++ 17 standard, a support was added to annotate the standard algorithm like standard sort, standard transform, standard reduce, standard accumulate, and so on, with a special parameter saying that these should be run in parallel. And that's pretty much it. If you have standard sort in your code, you can just add one more parameter setting execution policy, compile it with compatible compiler, and that's it. And as for compatible compilers, there is not lack of them. NVIDIA has their NVC++, AMD has their ROC STD power, Intel obviously includes that in their one API. And besides, there is this adaptive CPP project that we'll hear more about later when talking about SYCL. And it also offers a standard parallelism implementation, not limited to any single vendor. So here there is a distinction about source portability and binary portability, because code written in standard parallelism is portable, as it can be compiled with NVC++ and run on NVIDIA device, or OpenACC and run on AMD devices. But yes, the resulting binary is limited to a single target hardware. Adaptive-CP somewhat breaks that, because you can write, it can generate portable binaries that will just in time compile the code for any target supported, any supported target, be it AMD, NVIDIA, Intel, or even CPU. But it is not officially supported by any vendor, and it is somewhat less mature and less mature project. But having said that, in general, when dealing with standard parallelism, one should be cautious, because while standard parallelism implies that, it's part of C++ standard, it should be widely supported, it should be as uniform as it can get. That is far from true. The degree of support for different algorithms varies greatly. And for example, standard reduce can be supported by NVC++, but not by one API, or vice versa. And if you want to accelerate your algorithm, you need to check whether they are supported or not by a specific compiler, probably even compiler version. Now, the good news is that even if your algorithm is not supported, your program will not crash. It will just run on the CPU. Okay, your compiler cannot offload this algorithm to GPU, but that is still a valid C++ code. It can probably parallelize it on CPU, so it won't fail catastrophically. You won't get best performance, you probably won't get what you expect, but it will fail over gracefully. So how does it in practice work? So if you have very simple call to standard sort, here, so you have your standard C++ includes standard call to std sort operated on two iterators, begin and end of a vector. That will run the code serially. To run it in parallel on either CPU or GPU, whatever your compiler desires, you just add this one parameter saying that it can run in parallel and without, and in vectorized. It is parallelizable and vectorizable. So in this sense, it is very closely related to how say OpenMP work. You pretty much add just one line and your magic and your code speeds up. And probably also need to add a bunch of compiler flags and just hope that it is supported. But if you are lucky, that is it. But except that if for OpenMP usually are limited to parallelizing C-style for loops, here it's more about parallelizing the C++ style algorithms, and it is not limited to just basic algorithms like standard sort, because C++ library offers functions like transform, accumulate, for each, and such that can run custom functions. So pretty much, you can just define your own lambda function, pass it to std transform, add std execution par unsec there, and yes, it will offload your function, will run on the GPU. Now, the big limitation of this approach is that that's it. You don't have any more control over what happens. So it is quite limited. You cannot control data movement. You can't even ensure that the code will run on the GPU. You just say to the compiler to do its best. And, so it is kind of low effort, but also very low control model, but still allows for some flexibility, and we'll look at the examples later in this lesson. One important part is that there are different execution policies when you're specifying this parameter here. For GPUs, in most cases, you just want to use par and sec, which means that there are no dependencies between two loop or two different elements or which the algorithm is run. So it can be parallelized and vectorized as much as you want. And that's what most compilers support, and that's the property you anyway most likely want from your algorithm. Yeah, Kokkos, let's skip it. OpenCL. OpenCL is closer to what let's say true kernel-based model because it explicitly has kernels. They're even more explicit than in CUDA and in heap because they are stored in a separate file. And then they're pretty much read as text, or they could be stored as a string. They're passed to the runtime compiler, and that's it. So it's very manual, sort of low level, as in you need to do a lot of manual bookkeeping and initializing the data, copying, and you even need to manage in runtime how the code is compiled for your device. But also it is very portable. It was created in December 2008 as a standardized open alternative to CUDA, and it gained some traction since then. Not in the HPC world. They're usually for many years, the only relevant vendor of big data center GPUs was NVIDIA, and most people were writing their software on CUDA, and NVIDIA was very much invested in improving CUDA and not that much in OpenCL. But still, OpenCL was available there and worked on NVIDIA, AMD, and Intel GPUs on different flavors of integrated GPUs in your phones and whatever. Embedded devices, Raspberry Pi, you name it. So it was and is portable. It has FPGA backends. There are different implementations, say POCL, totally open source implementation targeting CPUs and NVIDIA GPUs. It is indeed quite portable, but also, it has in HPC world never gained traction and never received particular attention from the hardware vendors, and also for many years it was shunned by developers simply because it is low level and you just need to do a lot of manual things just to get the code running. So there are some instructions of how you could build OpenCL for Lumi. And usually you just load your module, your compiler, and just use it to compile and link with OpenCL. Compiling is actually very easy, but the actual programming is quite a chore. So first things first, you need to initialize your device, context, and queue. So device and queue is something you're familiar with from the non-portable model chapter. Device represents, well, a physical device, your GPU, or maybe a view of your CPU or your FPGA or whatever. And queue is what heap and CUDA call stream. Context is managed implicitly by CUDA and heap. In OpenCL, you need to manage it manually, and context is a memory arena. It's a single handle used to manage memory allocations and pointers. So it is just yet another thing to keep track of and yet another parameter to pass around. And if you think that, so this just gives you default device and pretty much prepares things to run there. It gets default device, creates context on this device so you can allocate memory and create something that interacts with this device, and then you create queue that you can use to launch it. And so that C++ API, OpenCL also has much widely supported C API that, of course, I cannot right now switch because my mouse decided not to work, but I can do it. Yeah, great for basic navigation. And if you think that 3 lines is not much, C++ API is not that widely supported. So if you want to run really portable code that works reliably, you probably want to use C API, and there it indeed becomes a chore. So you need to manually track all the errors. You call this get platform IDs. You create, first you need to get all the list of platforms. Say different platform is OpenCL providers. You get different platform for your Intel and NVIDIA devices. You check the errors, you get device IDs, create context. So you can see that it quickly becomes verbose, and here we just do what CUDA does with just 1 or even 0 lines of code. That is what CUDA pretty much does implicitly. It creates default device and creates queue on the device in CUDA. That's what you get just in your main already. You need to create a stream unless you want to launch multiple kernels in parallel, but in OpenCL you need it for any operations. And what is in a way neat in OpenCL that is not available in CUDA is the buffer-based programming model, because in CUDA and heap, and it's also possible in OpenCL, but that's basic low-level stuff. You may have to manually allocate the memory either on device or unified migratable, and you need to pass these pointers around. But this also means that you need to manually ensure that you don't have any data erase. For example, if you have 2 kernels operating on the same buffer, you, as the programmer, need to make sure that you don't get any data erase, any conflicts between them if you want to run these kernels concurrently. And alternatively, if you do want to run kernels concurrently, you need to carefully analyze their data access patterns. And if you get a complex application with many different types of kernels operating on many different types of data, that can quickly become very hard, or at least time-consuming. And buffers is a way to automate that. Basically, you don't just say, allocate some memory on the GPU and give me a pointer. You say, okay, here is the buffer of n integers, and now for this kernel, I want to get read access to it or to part of it. And for this kernel, I want to get write access to it. And for this, I want to get read-write access. And then the runtime knows the access pattern of your kernels. So it can automatically run them in parallel with each other. So if you have 2 kernels reading from the same input buffer, you don't need to bother too much with different queues and stream. You can create one out-of-order queue. You can use buffers, and that's it. And you just say that these 2 kernels need read access to that buffer, and the runtime will see that they can run in parallel. And if you have one kernel writing to the buffer and the next one reading from it, the runtime will automatically serialize them. So the second kernel will wait for the first one. And if you don't want this magic for your code, yeah, you can use what's called shared virtual memory, or SVM approach, introduced in OpenCL actually later than the buffer-based model. And that much closely mimics how the unified memory works in CUDA. So you, with again some extra bookkeeping with mine. Now, that was memory allocation. What about kernels? It said kernels in OpenCL are not just explicit, they are very much external to the source code of your application. If for small kernels, you usually just save them as strings in your code. For large kernels, you can keep them in files. There are also ways to pre-compile them and have a binary kernel available, but usually that's not what you want to use, especially if you strive for portability. So, and here is an example of a simple kernel that just fills the array with its own indices. And you can see that it's, in spirit, quite closely follows what you have CUDA. In CUDA, you would have, or heap, you would have global here. Here it's kernel. In CUDA, you don't have memory type annotation, but here you need to say that this is pointer to global memory. In CUDA, you would do the thread ID, IDXX plus block IDXX times blah, blah, blah. Here you have just single get global ID function, but other than that, that is very much how you would expect your kernel would look like. And there are even approaches, not widely used, but for some simple cases, quite functional, of using preprocessor defines to just replace, to substitute some keywords for either kernel or global, and this way the same code can be compiled for CUDA, heap, or OpenCL. Again, very limited still, but in simple cases that can work. But yeah, so you have your code as a string. How do you run it? Yeah, you need to compile it for a target device in runtime. So you need to create a program object. Then when you have the device, you need to build it. And the kernel can the program can contain several kernels. So then you need to extract the kernel by its name. A kernel source, pass into this OpenCL function, device, and functioning. Yeah, again, that's something you already get automatically by writing a CUDA kernel. Here you need to do it manually, and with C API, it gets even less palatable. And we'll look more at the complete examples later, but that's just to give you a feeling. Again, kernels themselves are very similar to CUDA, and you would expect that you have roughly the same features you have in CUDA, like shared memory, and obviously it's the same hardware underneath. So you still have to worry about, say, your memory access being efficient, coalesced, and such. You still have bank conflicts if you're running on the GPUs and not totally different hardware. You still need to care about block size, so it doesn't go anywhere. It's still very much like you would write your CUDA code, except the keywords are different. Probably some vendor-specific low-level function might not be available. And also, yeah, you need to just manage a lot of things manually. So last model that we'll talk about today is SYCL. It was proposed as a layer on top of OpenCL initially, but later it evolved into its own thing, not limited to OpenCL. It is, just like OpenCL, a vendor-neutral standard managed by Kronos Group, but it tries to bring all the convenience of CUDA, as I mentioned, all this manual bookkeeping with OpenCL that most people really don't want and don't like, and it's huge just impediment and creates a lot of friction. Yeah, what about if we create a standard that has all the nice bits of single source programming models like CUDA and heap, but yeah, it's not really vendor specific, is open, and that's what SYCL is. And there are two different, if OpenCL is usually works by a vendor providing just the library, so the code you don't need any support for OpenCL in the compiler because, well, your kernel is just a string. You just need to header and the library in the runtime to link and all the things. In SYCL, since it's single source, you need compiler support. And there are two major compilers that can deal with SYCL code. That is Intel One API and Adaptive CPP. So Intel One API, you have heard of it before, and it can it's supported obviously by Intel, but can target other hardware as well. So it is portable, even though it originates from a specific vendor. And Adaptive CPP, which you heard about earlier when talking about parallel STL, is an independent project from Heidelberg that also is quite portable and I would say rather feature complete. I'm talking about SYCL. So here are some build instructions, and then basically just take the compiler, say use fsql flag and give you a file. That's it. We'll build and execute. Get Intel devices because, well, it's Intel One API. But if you want to target NVIDIA or AMD, you need to install a separate plugin, totally free, and open source on GitHub. And just specify a target, or it can be multiple targets. And that's it. Similarly, for Adaptive CPP open source project, you download it, you compile it, and then you can just run ACP list of targets. So here we have one NVIDIA, one AMD GPU, and your program. Neat thing about Adaptive CPP, just like with parallel STL, is that it can use so-called generic mode. So instead of specific devices here, you can use ACP targets equals generic, and then it will compile your code to an intermediate bytecode, not limited to any single vendor, and then whether it is the resulting binary later on NVIDIA or AMD or Intel device GPUs, the code will be just-in-time compiled to suit the device. Obviously, again, as with any portability, you lose some of the ways to treat, you lose some of the way to use the low-level functionality, but you gain in that you have not only source code portability, but also binary portability. And that is also available on Lumi. So into some modules, you need to use a separate module file because it's not installed by supercomputer wide, but it's only installed by CSC. But anybody can use that. So you just module use and module load, and you have it. Sadly, the installation doesn't support parallel STL, which is why we don't have the instructions there. It's a bit more involved to compile Adaptive CPP with parallel STL support and with query compilers and with AMD on large machine. It gets quite complicated, and there hasn't been enough standard parallelism use cases to justify this effort. So, as I mentioned, SYCL originated from OpenCL, so you have some similar terms like context and queue, and what's in OpenCL is called SVM shared virtual memory. Here it's unified shared memory. It's a very related concept. But SYCL also does a lot of this bookkeeping automatically, so you don't need to create, for example, all this context. Default device, you can just go and create SYCL queue, and that will, it will create automatically create a context, find the default device, and such. So, closer to CUDA, you just can go straight to writing your GPU code and not bother first with 20 lines of initialization. But also, if you want, you can get the list of all devices and then iterate and get their properties, create queues with different features on each device, and run stuff on different devices. So if you want, you can use it, and it is very C++ heavy. So if CUDA is, even if it supports all the latest C++ features, the API itself feels very C-like. Here it is all the templates and namespaces, this kind of stuff. So one more thing to be afraid of if you're not familiar with C++, that could be a barrier sort. And just like OpenCL, in SYCL there are two modes of working with memory. You can use automatic buffer accessor models or pointer-based unified shared memory. So for buffer-based models, you just define a buffer. I have buffer of n integers, and then when you submit something to the device, you request, for example, write access to this buffer, store it as an accessor, and then in your parallel 4, you can write to this buffer. And similarly, if you later launch another kernel reading from it, it will automatically wait for this date. While if you launch another kernel that has nothing to do with this buffer, it will be able to run in parallel with this kernel because they don't have any data dependence. So you get this nice automatic, on one hand, parallelization because you don't need to launch kernels automatically. On the other hand, you get dependency tracking, so you are not sure when you have multiple kernels running in parallel on the same device. You don't need to bother with setting the dependencies between subsets. You get the data dependency graph just from your code. And as we'll see later in the examples, it also can be used to automatically move the data between CPU and GPU. And you just have buffer. If you look at the API, it's not really connected to any device. It's a buffer resides on the device or on host, or if you have multiple devices on a specific device. For example, here you need to access it on the device, so it will allocate the memory or move the memory there. And later, if you want to access the same buffer on another device or on host, the data will be implicitly copied. But if you want more control, you can, of course, use manual memory allocation. With malloc shared will allocate migratable memory that you can use in device and on host later, except, now it is just a pointer. You don't need to bother with defining accessor, but it also means that you don't get any of these benefits. You just have, just like in CUDA or heap, you have a pointer, you can access in kernel, you can later access in host, but then if it's shared memory, you don't need to copy it, but you still need to make sure that your access is synchronized. You still need to wait for the kernel to complete. But this way, it is very much like CUDA. You allocate memory. Here you say you want to submit an object to a queue. Object is a parallel 4. This is some boilerplate just to help you and the compiler and the debugger to give a name to this kernel. And here is pretty much the kernel body. So instead of having the kernel live separately as a separate function in CUDA or as a totally separate entity like a string in OpenCL, here you can use lambda functions as kernels. And here is a nice lambda function that just takes a single parameter that is thread index and does something with the v pointer. Let's time. So let's go through some of the examples. And here is simple parallel 4 with unified memory. So if you don't want to bother with data copies, here's how it looks. So with standard parallelism, it is very simple. You have some normal C++ vectors that can be filled somehow. And then you can launch, for example, STD transform to compute element-wise product, and just say this should be launched in parallel on vector A from the beginning to end, then also use vector B and output to vector C, and do this operation, input from vector A, vector B, output will be, the returned value will be stored in vector C, and we'll just launch this automatically element-wise on the contents of these 2 vectors, and if you compile it with the compatible compiler, it will do it on the GPU. If not, it will do it on CPU. And that's it. If you already have your code written like this, with standard transform, standard for each, standard reduce, transform, reduce, then it is very easy. But again, you see, you don't have any real control how the memory is allocated, how it's copied, it's moved. You fill it on host. This is launched somewhere on the device. You access it on host, but yeah. And also you can really launch multiple operations on the GPU in parallel or launch on different GPUs. So it is, in this sense, quite limited, but also very little effort if your code is already structured in a compatible way. And the same thing in OpenCL, just element-wise product. And here, we start with some includes. Here is our kernel code. Again, it's not actually, from the compiler point of view, any C++ code. It's just a string. And again, we have get global ID to get the thread index. And here we write C plus A times B for some specific integer arrays. And here we go. Here is all the fun initialization. So create platform, get list of platforms, get get the first GPU, create context, create command queue, create program from source, build program for the device, extract kernel from the program. So it was just getting started. Now we allocate memory. Then to launch the kernel, we set every single pointer. So we set every single argument. So we A, B, C. We need to set them manually here. First, second, third argument are set to A, B, C. We say that we want to access the SVM memory on host. We write them. Okay, we say we are done with that on host. Then we launch the kernel of certain size in certain queue given kernel. It's launching. Then we say, okay, we want to read the memory on host. And here again we do SVM map. We do whatever we want with SVM memory. In this case, print it, and we unmap. So again, the kernel itself is very similar to what you would write for CUDA, but a lot of things that CUDA does manually, because it still happens. Still the same underlying hardware, still same underlying mechanism. So it's not like CUDA is, from hardware point of view, strictly more efficient. All these things, all these contexts, they exist implicitly in CUDA. But just CUDA hides it from you. OpenCL just, okay, deal with it. And now SYCL. As you can see, it is much more concise, because it learned some lessons of OpenCL. Again, you do the include, but then you can just, for using the default device, you can create a queue, allocate, in this case, shared memory, n integers 3 times. And since it's shared memory, you just can fill it on host, launch a kernel on the device, n threads in total. In SYCL, you can either, and in OpenCL, you don't have to specify block size like you have in CUDA. For such simple kernels, you can just let it do automatically. But if you want, you can use ND-range construct to specify separately block size and grid size, like you do in this 3 chevron syntax with CUDA. And here is your kernel. Here is how you actually the math that is being done, and it's run on queue as a parallel 4. Parallel 4 on range n doing this function. And then it's unified memory, so you just print the things on the host again. No need to copy, but you do need to wait for the kernel to complete. It is pointers, memory allocations, and in the end, of course, be a good citizen and free the pointers. If you want, you can, here are some examples of using buffers. And here are the examples of launching multiple kernels in parallel. You can also take a look at the reduction. So if you want to have somewhat more complex algorithm, not just doing pairwise operations on the array, but for example, in this case, computing a sum of the array, here are some of the examples. And yeah, so to conclude, the big appeal of portable models is that, yeah, if you want to target different hardware, and in modern world, you probably do want that, you can avoid writing the code separately for each different device. You just write it once and you can run anywhere. But as a downside, yeah, CUDA is still the king of the hill. It's still the most popular platform. Most documentation is still there. A lot of well-optimized libraries is still only there. So, okay. Yeah, opting for some of those portable models means that you don't get all of it, although not quite. For example, in SYCL and in Kokkos, you can actually use the native library. So if your SYCL or Kokkos code is running on CUDA device, you can call whatever CUDA libraries are out there. Similarly for heap or for Intel. Obviously, if you are using QFFT, your code won't be portable. But if you really need to use FastFFT and you don't mind, for them, specializing parts of your code, that when you're running on NVIDIA, use that, you can do that. But still, yeah, its whole ecosystem is less mature, and that probably especially problematic when you're just starting, because you want to have nice error messages. You want to be able to Google your error messages. You want to see examples, code material, and such. That is not as popular. And for OpenCL, it is better, but still, yeah, super limited compared to CUDA. So, yeah, if we want to compare specific different, sorry? Okay. All the models discussed here. So SYCL and Kokkos, which is in many ways similar to SYCL, also use like different approach to how you compile and organize your code, but still in many ways also lambda-based. It's much higher level, and really you can avoid bothering with all the memory management, just use just buffers, and then you don't really need to think about, oh, GPU has its own memory, I need to copy things. You just say that you have this array, and please, dear runtime, deal with it. It will work. They're also very C++ heavy. So if you're comfortable with C++, that is not a problem. If you come from a different language, it might feel overwhelming. And yeah, relatively new, we are talking about like 5+ years for both of them. So yeah, not exactly newcomers, but again, compared to CUDA, not as widely used. OpenCL, on the other hand, is much more mature, is much more portable, because yeah, basically if you really want to run on your phone or on a Raspberry Pi and on MI250, and you want to use the same code, yeah, that is OpenCL. But if you want to run fast, might be more complicated, because again, very few vendors are actively, especially in HPC world, actively interested in improving their OpenCL backend. That's not their preferred frameworks. They most recommend their own. And OpenCL, unlike SYCL, which, for example, builds on top of CUDA and heap, so you just have another layer on top, but that still allows you to tap on the low-level functionality at the bottom if you're willing to sacrifice portability. OpenCL doesn't work like that. It's sort of separate stack, and if your vendor doesn't offer a library, an FFT library for OpenCL, then you're out of luck. Or, for example, doesn't offer some intrinsic, like my operation to use Tensor Core from OpenCL. If your vendor doesn't do that, nope, you cannot do that. In SYCL and Kokkos, you can use preprocessor to define if you are running on this vendor. Please use this operation for matrix multiplication, for example. So, yeah, and also OpenCL is very verbose. It might come out as somewhat petty, like, okay, we are doing HPC here. We can write some code, but in practice, yeah, it is huge barrier and huge annoyance for people, and I think it's one of the reasons OpenCL didn't really get a lot of traction. And standard parallelism, we decided to move it to the kernel-based models because in some cases, like standard for each, it kinda is, but also in other ways it is similar to directive-based models. So very high level of abstraction, very low way, very few ways to control your code execution and data movement. And while standard parallelism might sound like something that's widely supported, it most definitely is not. The support is quite sparse all over the compiler space, and also uneven. Some functions may be supported, for example, by NVIDIA compiler, but not by AMD, and vice versa. But things are improving, so if you're looking long term, it might be something to consider. And with that, let's go to the exercise. Sorry again for this stupid jumping around, but yeah, still doesn't work when sharing the screen. So the exercise will be in SYCL, because that's what I mostly work with. And honestly, among those models, I think it is nowadays most practical to use. And it will be a very well-known SexPy, single precision, alpha x plus y, vector addition and multiplication by scalar. So I will do this interactively, but you can go to Lumi and do as first, make sure you have your repository checked out and you get full origin main to bring it up to date. It is already up to date here. We do SL lock allocate for 1 hour on standard G1 GPU. Yep. Got the allocation. Now I can do module load dummy. Module use to get CSC modules. Module load. Now we load ROCm and ACPP modules. If you are finding it hard to follow, don't fret. It's all here in the document. Loaded. Here we can run the ACPP info. This is adepcp tool to get the list of available target devices, and you need to launch it with srun because right now you're on the login node and you want to run it on the backend node. If you just launch it without srun, you will have no devices. If you launch this srun, it will run on the compute node, and you will get this nice MI250X GPU available to you. Oh, alternatively, say semi, of course. Okay, it's zoomed in, so a bit screwed up, but you can still see that there is one GPU available. And now content examples, non-portable actually kernel models. There are all the code examples here. Okay, one was crashed. All the code examples featured in the lesson, and actually there is also some of the examples from the non-portable section translated into SYCL and OpenCL and Kokkos. So in the non-portable kernel modes, there are also some examples with SYCL. If you want to compare side by side how the same code looks, SYCL or OpenCL and heap. So, but let's go into the exercise. First, we can compile SYCL unified memory CPP. Unified memory, so we can compile one of the examples just to make sure that it works. Takes a while, especially first time. Yeah, and now you can srun the memory. Yeah, and it runs, and it runs actually on the GPU. But so you can play around, try compiling the SYCL or OpenCL example. So if you want, you can also run CC CL kernel-CL CL kernels. Some warnings, but that is quite minor just because we are using somewhat older but still supported API. It's different programs, so that will be different, but still, yeah. You can check that it runs and the output is as expected, and yes, that is expected. But yeah, if you are fine just running things, you can look at the exercise. And here we have most of the code in place, so it creates a queue in order so you don't have to worry about synchronizing things, prints some basic info, and now it allocates some memory, but not all, so you need to fix the memory allocation, fix the initialization, handle copies, because here we are using separate device host model. Here is your kernel. You would need to slightly modify it. copy the data by generated. And here's some code that just checks things and frees the memory. And also it has a couple of questions here that you can use to check your knowledge of how things work. I won't check you, it's strictly for your own use. So you can try looking at this, trying to fill in the blanks, and similarly compile it. ACPP size. And it won't compile right now. Some of the bits are missing. Yeah. But that's what you need to do in this exercise. And if you get stuck, you can ask questions, or also there is exercise solution that you can always take a look at, and it also contains answers to the bonus questions. So if you're afraid of spoilers, don't look there. So previously you have seen it done with CUDA, and you have seen it done in CUDA like this using shared memory. So you get it arranged like this. You have stepwise reduction, this thread gathering adding up values from these two, this one from these two, then repeated few more steps until you get only one data. And yeah, if you're familiar with floating point, you might notice that you have different ordering of operations compared to just 6 plus 7 plus 1 plus minus 5 plus 9, blah, blah, blah. And for floating point, it can change the result, but such is life, and usually reordering of floating point operations is unavoidable in parallel algorithms, so we have to just deal with it. And here is an OpenCL kernel that does spiritually same thing. So here we have in our kernel stored as a string, or you can store it in a separate file and just read this file in and pass it to the OpenCL API. But here let's look at this kernel. In kernel or global just designates that this function is a kernel, not some helper function for example. So it is itself something that can be called from CPU to run on GPU. Just like in CUDA or heap, the kernels must return void. And unlike CUDA and heap, you need to indicate which kind of pointers it is. So this pointer to sum is pointer to the global or device memory. And this local mem pointer is pointer to local or block specific memory. Here, first things first, if you're lost in the woods, you need to first try to understand where you are. Similarly here, when you start a thread on a GPU, the thread first you need to know where it is in the global grid of threads. Again, just like in CUDA, you usually start with query thread IDX and block IDX special variables. Here you can use get local ID to know the thread index in a block, or using OpenCL parlance, that's work item index within work group. L size, local size, work group size is the block size in CUDA, blockdim.x. And global size and global ID don't have direct correspondence to CUDA, but they can be computed by thread IDXX plus block IDXX times block dimx. So it's basically again a very repeated pattern in CUDA of just computing the thread index in the grid, global thread index, and here we just get the number of threads in total. So we know who we are and where we are. Now let's start doing things. First, we store the original memory. We just write our global ID to the local memory array of the local ID. That's just an assignment, nothing fancy here. And since that we have multiple threads writing to an array, each writes their own element, but we cannot assume that they're all executed at the same time. So since later we read the data written to this array by different threads, we need to have a barrier. It's sync threads in CUDA. It's barrier. CLK local mem fence here. Yeah, barrier. We need for all threads to wait for all other threads within the same block. We cannot do global synchronizations. Again, just like in CUDA. Within the same block. And afterwards, yeah, we know all the threads has written their original values to this array. We can do the reduction, and just like here, first thread reads its own value and the value of the thread plus, in this case, 4, then plus 2, then plus 1, and then that's it. So plus S. Okay, here actually goes a bit. It's not the same implementation, but it's a bit inverted. So first we read from these two arrays, and this reads from these two, this from these two, and then we reduce the other way. But anyways, it's the same approach inverted. So we check if it's one of the, in this case, even threads, and we are not running over the array. For the local memory, we add the value of its neighbor to the right. Okay, so we did the first step of the reduction. And again, since we modify the local memory and later want to access it, we need to this barrier. Then second step, we multiply S by 2. So the first thread number 0, we read here its value and the value of thread number 2. So thread number 0 contains value from threads 1 and 0 and 1. Thread number 2 now contains, after the first step, values from thread number 2 and 3. So in this step, we'll add the values of 0, 1, 2, 3 together. And that's what we do, because thread number 0 has this condition satisfied and this condition assuming satisfied. Again, we wait, and we repeat it until we're at the very end, and we added all the values that are available in the local memory. And now the very first thread in the workgroup and local ID equals to 0. So we only need one thread which contains, after all these steps, the sum of the local array. And we do atomic add on the global memory so that when we have multiple blocks doing this reduction, I think the value here, yeah, we only have 10 in this example, so there will be only one block, but we have multiple blocks, they will have many thousand of values. We'll run multiple blocks, so within each block we can use local memory to do this reduction very efficiently, because local memory or shared memory in CUDA is very fast, almost as fast as registers, but also it's shared with neighboring threads, but that only works within block. So if we want to add value between blocks, we unfortunately cannot use these fast ways. We can just like read things. We need to use atomic operations on global memory, and that's what we do. So if we have, for example, 1,000 blocks running with 1,000 threads, in total reduced to 1 million values, first each block will do the reduction in around 10 steps here, binary logarithm of 1,000. And then we'll have 1000 atomic heads, one from each block or workgroup, adding things to the global accumulator. So that is kernel. Very similar to what happens here. So we're using atomic head approach. And here is how the main looks like. Here we are using the C++ API, which is in OpenCL still verbose, but not as verbose as C. We get default device, create context, and create queues. Is pretty much everybody just copy paste the thing because it's roughly the same. Then we create program using the kernel source. We take this variable string. We compile it just in time for the specific device. So your program, your binary ships just with this thing hard coded, and when you launch the program, it is compiled for specific GPU, and you create a kernel object that you can use to reference. And here, well, you actually start doing things. So you initialize the size of the reduction problem and the target variable, and for it you create a buffer referencing this original variable, and this buffer basically means, yeah, okay, we have this host memory and we want to use it original location. We use this context for memory management allocation tracking, and it will be read-write memory. And yeah, so we say to OpenCL runtime, yeah, create this object, represents some memory, and do whatever you need with that. Then we take our kernel object and say, okay, first argument is buffer, second is used to just indicate that there should be some local memory allocated, and then we with one integer per thread. And then we launch this kernel reduce, null range, blah, blah, blah. We don't want to specify specific block size. We just say, okay, there will be some block size, but you are free to choose whichever works best for you for the runtime, because our algorithm doesn't impose specific block size. And then we have this enqueue read buffer. It is launched in the same queue and wants to read the buffer that was previously written to, so it will automatically be serialized to launch. The copy will launch only after the kernel finishes. It will be blocking. It will read only one integer into this sum variable, and since it's blocking the this will finish only after the copy is done, and then, yep, that's it. We can print the value. And if you look at SYCL, SYCL as a higher level model actually has some affordances to make programmers' life easier. And similarly for reduction, it actually offers a reducer object with a somewhat not easy to parse syntax, but the one that saves you a lot of effort if you know how to use it. So here, again, we don't really need even to write our own kernel for reduction, because it is part of the languages. Like for, say, OpenMP, you can just add an annotation that you want to reduce to accumulate into this variable using plus operation. It's spiritually similar here. You just say you need, in your kernel, you would need to do the reduction into this buffer using the plus operation on integers, or it can be some custom lambda function here. And then you launch your parallel for kernel, passing this reducer helper, and you just use the combine method and say that, okay, from this thread, we use this value. In this case, it's just its global index. And then the compiler will automatically see that, okay, we need to do the reduction of these values into reducer, some reduction into this buffer. And then this buffer is created using the host pointer. So when the buffer is destroyed, because it goes out of scope, we can just print the value of this variable because it will be copied back automatically. So that's, but also, of course, you can write the reduction manually if, just like with OpenCL, if you really want it and you think you can do better job than the standard library. Which for some special cases, it's quite doable. Because standard library tries to be generic and not necessarily use all the optimizations if you have like some interesting properties in your data.
Yes.
Want to follow, there is this matrix, I suppose, that follows the same logic as the CUDA, progressively making more complicated. Making the kernel more complicated and hopefully more efficient. So yeah. Now I think we have a break, so we won't know how this thing runs, perhaps because it takes ages to compile, and I don't want to delay your lunch, but okay, it's done. But you can definitely try experimenting with this thing yourself and seeing the bandwidth and performance of different ways to do the matrix transpose on the AMD device and compare maybe with native heap. If you want, can compare with CUDA, obviously, but still something.
This afternoon, it will be me and my colleagues Hicham, and also talk about the high-level programming language part. Yes, and this is the lesson material. And before the discussion, I think we can before the lecture, we can have a discussion. So let me know, have you ever used the Python for programming and data analysis, or have you ever used Julia for programming or data analysis? If yes, what is the frequency, or almost daily use or randomly use it? You can type O right here, for example. Yes, O, that I know just the one person can use this. And if you have other numbers, you can type it right here, and how frequently you use Python, you use Julia for the programming, data analysis, or some other works. Matplotlib, great. This is the good. I use it daily for the data visualization. Okay, I can see more people using Python. I suspected. Never use Julia. Okay, but I will show you how to use it. It's somewhat quite simple, and kind of faster than Python, if you're familiar with this. Okay, come back to this later. I think I will talk about this high-level language support. So suppose we learned about the GPU programming, various models, portable models, and non-portable models, and direct models. Suppose that you never come to this programming before, and you just use Python or Julia for the data analysis. So the question, if you have, can we post the code of the script written in Python and Julia for the language for the GPU programming? The answer is yes. It is relatively simple. I will show you how it will work. So we talk about Julia. Julia is a kind of a modern high-level programming language that is fast it's fast, easy to write. Fast means it's comparable to the traditional HPC program language, for example, C and Fortran. Relatively easy means it is human readable, means similar to the Python. It can get the meaning directly from the command. Julia 8 is the first class support for GPU programming. And through the following packages, you can see that these packages are window dependent. For NVIDIA GPU, it's CUDA.gl. GL is the for the Julia. So for AMD GPU, it's so simple. AMD GPU. For Intel GPU, is one API.gl. And for the Mac series, it's the M series, it's the Metal.gl. For these packages, I can say the CUDA is quite much more mature than the other three packages. So if you are quite familiar with, if you have access to NVIDIA GPU, you're good to use it more. If no, you can try to use AMD GPU or others. If you're a Mac computer, you can use the Metal.gl. I use it in my local computer. It works well. The APIs of these libraries are quite similar, so it is quite easy to translate between them. Suppose that previously you used CUDA.gl, but now you have to use AMD GPU.gl for some reasons, then you can do straightforward translation about your Julia script from CUDA.gl to AMD.gl. How to use these packages? First, you need to install these packages using the Julia Package Manager for the PKG right here. Here I just use this demo here. You need to install AMD GPU.gl, and the command will like this using PKG and the PKG add this, and then you can use it. Later in the type along, I will show you how to use these packages, mainly for the AMD GPU. Once these packages are installed, we should know some basics about these packages. And here, four basic aspects are covered. That is if you see, the array interface, the window libraries, the high order abstraction, and also you can also try to write your own kernels and then launch your kernels in the script. Yes, for the array interface, for the array interface for the GPU part, it is quite same, almost the same to that in the CPU part. For the CPU part, we can use this regular base array. That array is to create an array. It can be array here. It can be it is similar to the list in Python. So for CUDA NVIDIA GPU, it has the cool array. You can see from the name, you can figure it out. For AMD GPU, it's ROC array, and one API, it is one array, and for the Mac GPUs, it's the Metal array. Well, you just replace the one with the keyword like this, and it's quite straightforward to use it. Here we take the AMD GPU, for example, and this to see how we're going to have a simple operation later on the type along part. And see, we're going to use AMD GPU, use this package, and this ROC array is to generate array at the GPU part. You can see this is a list. Generally, this is array, and you can generate at this is array at the CPU part. If you run this command right here, and then you can transfer the data from CPU part to the GPU part. AD is the array on the GPU. And then you can do this arithmetic calculation, which means that each atom in this array will add 1. After this calculation, you can fetch the data back from GPU to CPU. Then you can use this array. This is the regular array in Julia. When we can use it to create 1D array or multi-dimensional arrays. Somewhat simple, right? It is. And if you use other GPUs, for example, NVIDIA GPU is CUDA, it is CUDA array. Just to replace the keyword added here to the response. Intel is just one array and Apple is metal array. Yes, we can see a second example about how can we do this matrix multiplication. We also take this AMD part, for example. First, here we are going to use a benchmark tool, this package, to benchmark how efficiency if we use the GPU for the programming. First, we'll generate an array. This is the size of this array and randomly. And this generation is on the CPU part. And later we use ROC array to transfer the data from CPU to GPU. And then we do the benchmark. The first one is the multiplication of two arrays at running on the CPU part. And for the GPU part, we write a loop right here. This array times the multiplication of two array. And then later we use the synchronize to make sure that once all threads are finalized, then we can get take the timer. Yes, and then I will leave this to you, and you run the exercise to tell me what is the time difference and how can you figure out. You can change the size of this array, and you can get a different result. Yeah, this is how to run this Julia script. Actually, for this matrix multiplication, I should have said that there's no necessary for you to build everything from scratch. There's a lot of libraries that you can use. For example, if you perform the fast Fourier transform FFT, for the CUDA GPU, you can use cuFFT. It's really available at the CUDA.gl. You can directly use it. For the others, for example, matrix multiplication, you can use cuPlus right here. And also for linear solvers, you can use this one. For AMD GPU, we have also some ROC libraries. For example, ROC Plus or ROC FFT. Yeah, from name, you can see that this is specially developed from the AMD GPU. And so the others, you might come to these libraries when you're going to use these libraries in your script. Third was high order abstraction. So a powerful way for the GPU programming with arrays is that Julia can provide high order array abstractions. For example, in the previous code, we run this command to make sure that each item in this array we add one. And actually, for the Julia can provide a more general construct like broadcast, map, reduce, accumulate. If you come to the morning session, but the portable kernel-based, you know what is reduce and what is accumulate, and this is similar to that one, and also map. But if you're familiar with Python, this map is to select some items with some conditions and then get the new result. Well, actually, you can also write your own kernels and also launch these kernels. And also launch these kernels at your Python script. But the key issue is that you should know how to map your data from the matrix to the GPU thread. Yesterday, we come to this mapping scheme right here. We have the data matrix right here, and each one should be mapped to a specific thread. For this thread in GPU, it has its own specific thread index and the block index. So you know the one-to-one mapping relationship, so that you can find this item from the GPU part. For actually say that for NVIDIA GPU, it uses block index and the thread index for the indexing. For AMD GPU, you can see that it uses another word for word item index. But just the difference in name, but the procedure is the same. It can extract the specific information for each atom right here. Here we have provided like example for the vector addition using different GPUs. We also take the AMD version, for example. Here we use this AMD GPU. We define a kernel. We can say it is a function. Vector addition, something. At first, we create two arrays. We use rock array, means that we create these two arrays on the GPU part. Similar is a method that we going to create a utilized mutable array. This array has a similar size and type to the array A. Means C and A are the same, with the same size and same type. Here we choose the number of threads 256, and with this one, just this one is just for the efficiency consideration. With this number of threads, we can decide how many blocks we are going to use if we handle the matrix multiplication or matrix addition. And then we call the log number of threads right here, number of blocks right here, and then we launch this kernel. In this kernel, we can see that each atom in A array or A matrix, we then add the corresponding atom in B matrix or B array, then we can get the new result and put this into C matrix or C array, and then finalize this part. At the end, we will make a station to see if all atoms, all values in this array C or in this matrix C is equal to 0. So can you figure out if this what you can get, true or false? So I believe it's to you, and then you can tell me what you can get. For the Julia part, there are some restrictions in the kernel programming. Here it is said that with the kernels, most Julia support, with the exception of functionality that require Julia runtime libraries. These times maybe not work. Cannot allocate memories or perform dynamics functional calls. And well, this there are some restrictions if you go through the website of the Julia to see how if there are possible ways to handle this. If no, probably you have to seek more possibilities to handle it. Another thing is that for this Julia, it is more efficient to handle 1D array, 2D matrix, and 3D matrix. If you have this matrix, it is better to launch the kernel with specifically almost the same matrix from the GPU part. I mean, this is just you can have a one-to-one map from your data to the GPU thread, the GPU blocks, a GPU thread. Then you can get relatively straightforward information from there. Yes, this is I cannot say general description about Julia because we are not touching the basics about Julia. But if you want to, if you're interested on this aspect and if you want to learn more about Julia, we have a workshop on December 9, I think so. So you can come to us and we will show you how the basics of Julia, basic syntax of Julia, and how can we run the Julia using HPC resources. Yeah. Second part, let's talk about Python. I can see from this discussion, more people using Python. Oh, it's good because which means that not necessary for me to talk about is Python and the basics of Python. Here we mainly focus on the ecosystem of Python for GPU programming. There are multiple libraries right here. I just mentioned 4. PyPy is a non-Py, SciPy compatible data array library used for GPU programming. Originally, it was developed by NVIDIA GPU, but now it's experimentally support AMD GPU. Means Yeah, you can use AMD GPU to run this, to use CuDA. As I can say that if from the manual or official website, you can see that if you are quite familiar with NumPy and SciPy, you use this libraries in your script, it's really straightforward. You can directly replace NumPy with CuDA and with SciPy, replace the SciPy with the CuDA x.scipy. This is just a replacement, simple replacement. So that's not necessary for you to struggle the internals, the details about in this library. You can just a simple replacement like this. Second is I think a CUDA. I don't know how to pronounce this as data framework. CUDA version of data framework. This belongs to a package named Rapids. It provides pandas-like API. So if you use pandas in your as a script, you can accelerate your work even without knowing what is CUDA data frame or CUDA data frame. Well, just a simple replacement. PyCUDA. PyCUDA is a Python programming environment for CUDA. It is powerful, but theoretically it runs just on NVIDIA GPUs. And you need to have the knowledge about the CUDA programming. What is the CUDA programming? Means that you generate the data on the CPU part, you transfer data from CPU to GPU, doing the arithmetic calculation, launch the kernel at the GPU, doing the arithmetic calculation, and then take data from GPU to CPU. And this is the whole process for the GPU programming. I think we have mentioned this before, so this is similar to the previous procedure. Number is Number is an open sourced JIT, just-in-time compiler that can translate the Python code and the NumPy code into a fast machine code. So NumPy supports AMD GPUs, but it's quite pity that NumPy supported AMD GPU into the version of 0.53. Until then, we expect to have other packages for GPU programming, but we cannot make sure. So let's see what's going to happen from NumPy. But here, let's see how NumPy works. We here mainly focus on several decorators. Decorators means ufunc and generalized ufunc. Ufunc and generalized ufunc are easy way to run the GPU using NumPy. And it requires a minimal understanding of GPU programming, means there's no precise. Generate data, transfer data, launch the kernel, and take data from take data from GPU to CPU. We have I think 2 examples right here. The first, we have 1 example right here. The first is do a simple mathematical calculation, means mass power to x with the power of 3 and mass sin of this simple calculation. This is a regular Python version, import mass and define the function like this, and to call this, make it call, and you can get the results. It's relatively easy. If we use ufunc on the CPU part, it's also somewhat easy. You can see from the function part, you can figure out this is the same. But we just add a new line right here. Yes, here we use a number vectorize to produce the ufunc like object. From here, you can see that for these 2 variables, we have the specific type, which is number float type. And this is also the float type. And target the CPU means we are going to use the CPU for the computation. If you replace the CPU with CUDA, you are going to use CUDA NVIDIA GPU to do the computation. Here is another version you can see, but the name is a little bit different, just to figure out which function we're going to call. The target, the other is almost the same. number vectorize, and the float type 2, and then target is CUDA. Yes, it's somewhat easy. You can just provide 2 additional lines using number vectorize to accelerate the computation. We can benchmark these 3 methods to see what is the efficiency for this method. For regular Python, when we tested it, we got 6 SYCL. When we run this computation, we generate 2 arrays here do this arithmetic calculation. And if we use number for using CPU, we got 334 millisecond. If you see this is 6 seconds, this is 0.7 second. Can see this 10 times, almost 10 times faster than the regular Python. If you use a GPU, and again, we can accelerate the computation. If you see this is 700 or something, and this is 70, 80 something, and is again, we can get approximately 10 times faster than the number CPU computation. We should notice that here we use number vectorize for the computation, and number vectorize is quite limited to scalar argument, which can be rows, columns, as one-dimensional color argument for this function. And for multi-dimensional arrays or matrices, you can use generalized GU vectorize, and this is quite a convenient way for the data allocation. Yes, and for the data matrix multiplication, as I mentioned before, you can do this you can build everything from the scratch, but it's not highly not recommended because it takes lots of time and energy for you. Because there are lots of libraries, they have this, they provide to how to perform this matrix multiplication, matrix addition, or divisions like this. So, but here we just with these examples, we just to see how can we build this function like this. Regular Python, it is like this, and matrix multiplication, but 2 matrices and get a new result. This new result will be stored to a new matrix. If we use number GU func CPU version, it is this part is the same. It's similar to the regular Python version. And you can just add 1 line right here. Here we use GU vectorize right here. And this is just float type. And this means we're going to how can we run this multiplication. For the first matrix is the 1 row, the second is 1 column. I get a new result put in the new matrix. Then target is CPU. And if you use number GPU, the target is CUDA. Again, doing the benchmark, then you can generate 2 matrices right here, and then you can time it to see regular Python script and the number with CPU, number with GPU, how long it takes to run these computations right here. I will leave this to you during the exercise, so you can tell me, you can leave your comment at the hacking document and let me know the time, how long it takes for this 3 method right here. Yes, number actually, it is quite powerful because number can automatically do a lot of things for you. For example, the allocated memories on the GPU. There's no necessary for you to do this. Number can automatically allocate memory, get the data from CPU, and do the arithmetic calculation. And when the data was taken from GPU to CPU, number will automatically release this memory right there. And yeah, copy data from CPU to GPU, launch kernels, and data copy back, and then release the allocated memory. So everything number can take care of it, but the cost is that the performance might be not so high or not so good because this is the automatic handling of data transfer from CPU to GPU and from GPU to CPU and also the launch the kernels. Yes, I think we am gonna to stop here. We can play. I will have a tap along to show you how to run the exercises on Lumi. Before I leave, I will show you that we have additional lesson materials right here. Introduction to programming using Julia from us, and Julia for HPC, high performance computing, and Julia for HPDA, mainly for the data analysis. From our collaborators, for example, NICE, RIMAC, OpenACC, they have the introduction to run R, Python, Julia, and also MATLAB. You can click this. You can click this link. You can come to the right lesson materials. You can also follow these lesson materials for self-learning. For Python, we have the HPDA, the high performance data analysis, and the practical intro to programming using Python. This is 1 hour webinar we gave, I think it's 1 month ago, and we use the Jupyter notebook for the demo, and everything is right here. If you are interested, you can download this Jupyter notebook to your personal computer and run the exercises right there. Yeah, HPC using Python in HPC environment, and also we have also the Python for scientific computing. This we don't use GPU for this part, but if you can create a Python programming environment in your local computer, then you can follow the exercises right here to run to play the code using your personal computer. Yes, I'm going to, if you have more concerns, questions, you can leave your questions at the comment, and I will check them later. And now I will switch to this computer for type along. You can follow me for this type along, and if you going to follow, if you follow my type along, you can let me know if you miss somewhere, so I can stop and try to give you a clear identification. The left is the web browser. I'm going to log in to Lumi with this one. The right is the lesson material. If you come to this lesson material, there's set up per request, set up right here. We are going to use this we are going to copy paste something from this web page. Yes, and for the left is how to log into Lumi. It is lumi.cnc.fi.public. I can copy paste to at the chat box right here. You can also get together with me. Go to login, the left part, and I'm going to use login my access ID. I think you all know this, how to log in. That's one thing. It take sec. Yes. If you see this web browser, this container web browser means that you are coming to the Lumi. For the Julia part, I'm going to use subscript to see how to run the script, how to run the exercises. We're going to log in node shell. I'm going to choose this one. Okay, you can see. Give me a sec. I'm going to move this bar to the upper part. Yes, you can see I'm coming to Lumi. Where am I? I'm right here. I'm going to another directory, the CD scratch and project 46500131. This is the project number for us for the training. Right here, if you follow me, you can just come to this one, to see this directory. And I will create directory for myself. Make Julia. Yes. I'm right here. So then I will come to this lesson material. Oh, by the way, how about the font size? Should I increase it a little bit? Give me a hint, either yes or no. Yes. Yes, now it should be okay. Yes, and I'm going to this section, running Julia on Lumi. And I need to prepare 3 documents right here. One is project.toml. I just copy paste to save some time. Vi project.toml. As we are going to use AMD GPU and with the specific hash key, meaning specific version. So I copy paste this and copy paste at this document. Let's save it. And yeah, you can interrupt me anytime if you cannot follow. Second is the script. Before script, I think I prepare a submit.h. Submit.sh. This is the script we are going to use to submit the job on Lumi. Some content from the previous part, you can see we copy paste something right here, but not the S1 line. Yes. Oh, I don't need this. And then we come back to the Julia part and copy paste these additional lines and attach these lines to this document. In this one, I'm going to use one node and one GPU, and the in task is just one task. Time is okay, 1 hour. And besides the CPU, I also need, besides GPU, I also need a CPU. Here I ask for 2 CPU cores. And each CPU, I ask the memory of this megabyte. Module use the modules in this module and then load Julia AMD GPU. Here, I typed using PKG right here because I'm not going to include this part as the Julia script. I just type around here. And then I create a script of GL. Later, I will show. Yes, it's done. Just save it. And I need a script.gl. And then I'll copy everything from here. Yes. Here I use AMD GPU and generate one array, one matrix. The size is the size of matrix A, and then I'll copy this array from CPU to GPU. Here is AMD ROG array, as I mentioned before. Then I do this matrix multiplication and save it there. I don't want to get anything from this arithmetic calculation. After this calculation is done, I need to print a new line. Oh, EOF means end of this file. If I can get something in the result, I can make sure that this script will get run well. Save it. If you see, now I have 3 files right here, project.tomom, script, and submit. If there's no first issues, I will submit this. Splash, submit. Yes, now it's submitted. Let's wait if we can. If you see it is running SYCL -me. Yes, it is running 22 sec. We can see what we get from this example job that error info. This, we are going to load this module like this and also log for AMD GPU. And then it is running. I think it takes minutes. When we can get the EOF at the example job O document. Let's clear this tail example to see. There's okay. There's something update at the example E document. You see, this will install the AMD GPU and lots of dependent libraries. For example, abstract FFT, accelerate, array interface. If I just let me. Oh. Yes. You can see lots of dependent libraries are installed because AMD GPU need these dependent libraries for the computing. Array specific static array. Yes, you can see. Usually when first time you write, it will install these dependencies and also AMD GPU library. The second time, if you submit it again, there's no necessary to install. So the second time, the computation is quite fast, just a server sec. Yes, I got something at the O document. If I see it at O, I got this. End of this file means that the computation is done and everything is correct. There's no error. And it just need to install the AMD GPU library for a while. And otherwise, there's no special things for the installation. This is for the Julia example. You can play the code. You can run the exercise later. And I'm going to show you the Python part, how to run it. And this time I'm going to use another right here. You can see you can try to use Julia Jupyter, and also for Python, I'm going to use this one, Jupyter, for the as the programming environment. Yes, give me a sec. If I click it, it takes several. Yes, then Jupyter is here. The project number, interactive. This is the way for the interactive allocation. Number of CPU core, 1 is okay. 4 hour, not necessary. Just to say 20 minutes is okay for me. Setting, I'm coming to my own directory, and we're going to use Clay Python 3.10.10 as an interpreter. The Julia environment, not for me, and then I launch, and I wait. Yeah, patient, because your job is still the allocation in the queue. Usually it will take several sec. Now it's done. Yes, I think so. currently starting. Just wait several seconds. Yeah, now it is done. I've got this allocated ID from here, then connected to Jupyter. If you're quite familiar with use Jupyter Lab or Jupyter Notebook, then it is as it is. Yes, I copy paste something yesterday from the lesson material. This is the we defined how to run this simple arithmetic calculation. Now I just as a show the type along, I just click this button to run this cell. And the second, doing this calculation, I want to change another one to see if I get yes the new result. And to do the matrix multiplication, generate two matrices, and then to see how long it takes for this computation. Previously, it was 6.75 sec. Let's see this one. Yeah, well, much better, 4.6 sec. For the exercises, for the person part, you can copy paste everything from the lesson material and run this right at here. Yep, this is the type along for Julia and the Python. I think I will leave it to you to run the exercises and let me know the output, the result from your computation. I can leave your result at the shared document. Yes, let's run the exercises for 10 minutes. We can come back at 57, 58. Then we will have the exercise about heap Python. And Hacham will talk about the heap Python, how to see some lecture sessions and also some exercises. Yeah, right now let's focus on the exercises, Julia, and also regular Python. If you are lost somewhere, please let me know and I will repeat some part.
Yes. Yeah. By the way, my name is Hisham Magni, and I'm from University of Bergen. So this will be a short presentation. I got only 15 minutes. So I will complement what you have seen so far this morning. I mean yesterday, and also from Yongli about Julia and other high-level GPU programming model. So I will complement that by talking a little bit about heap Python. So you get many options, so you can choose which one you feel comfortable with, so you can implement in your daily work. The motivation you heard it in this morning is that Python is widely used in scientific computing and also in machine learning and related fields. So it seems like it becomes important that Python users should have GPU programming capability that they could accelerate their Python-based applications. So, and this is very important, in particular for those who are not familiar with C, C++. So it can be a bit challenging to write codes with heap C++. So I think having Python interface from which you can interact directly with the heap libraries that are written with C++ is really very important. So that's why I think I will heap Python. It comes in this direction, and what I will be focused on is some basic functions that I believe could be relevant in your case to start with implementing heap Python. So some basic thing. I will be focused on these 4 points. If I have enough time, I can tell a little bit about the fourth point, but I will focus mostly on the first 3 points. So I will tell you a little bit about how you can access the GPU properties from Python interface, how you can get many different properties. I will tell you a little bit about the GPU management. It means how you can allocate GPU memory, how deallocate GPU memory from Python, and also how you can copy data between a host and the GPU. And the last point is an example in how you can run some math library that are optimized for AMD GPU. And as I said, if I have enough time, I can briefly tell you about how you can compile and launch GPU kernels from Python interface. So these are the major points that I will try to address in these 15 minutes. So first, what is heap Python? Heap Python is a Python wrapper. Python wrapper, you can think about it as a piece of code or another layer that will help you interact with other programs that are written with C, C++, or even Fortran. So in this case, heap Python is a Python wrapper that allow you to interact with heap runtime API. So when I say here heap runtime API, so all the functions that help you to do memory management, launching kernels, in particular, as you can see, from heap runtime API, you can access the device properties. There are some functions that would help you to do that. You can allocate and deallocate the memory on the GPU. So you can copy data between CPU and the GPU, and you can even launch kernels from Python. So with the heap runtime API, you can do all these things. Heap Python also is a Python wrapper for heap runtime compilation, heap RTS. So this is basically what will enable you to compile GPU kernels at the runtime, meaning that during the execution of the application, and even more with heap Python, you can even run some math libraries that are optimized for AMD GPUs. But even more, you can do some multiple GPUs with RCL library. And the interesting also about heap Python is it's supported by both AMD and NVIDIA. So these are this is the thing that I will try to cover in this presentation. So let's start first by the how you can do GPU management from Python interface. So there are here basically two functions that you can use to access all the properties that are available, that are already available there. So we will start first by the first function. So the first function, heap get device properties, this is a function that accepts this object as an argument, and by passing that to the heap get function get device properties function, you can get a selection of GPU properties. Here I have a couple of attributes that I have listed here as an example, where we can print them out by running this Python script. And the first thing, obviously, is you need heap Python. So here we import heap Python. This is basically, we are here in the context of heap runtime API, and that's where we can access these functions. So the example here, what we want to access, for instance, the name of the GPU. We want also, for instance, to get the architecture of the GPU. What is the ID device of the GPU? You can even get the total memory of that GPU and even the L2 cache, if that's interesting. So if we run this simple example, by the way, this is subject of example 1 that you can access from the Git repo, or you can get it directly from the project directory. So the output of this script is the output of the script. You can see that the name of the GPU is AMD MI250X. The architecture of the GPU is GFX90A. There are some additional options here. So the first option is basically ECC memory, that's correction and checking of the GPU memory. And you get an additional option here. So this is basically a feature about a managed memory that by default is not, I mean, here you can see the sign. It means this feature is disabled, meaning that the page migration is not enabled by default. You have to enable it by exporting an environment variable. So that's not the topic of this presentation. So you can get more information about this feature in the link. So now, since we are running this on a single GPU, so the ID device here is 0. And you get the total memory here. This is in bytes, and that's equivalent to 64 gigabinary bytes. And the L2 cache memory is about 8 mega. So this is some of the properties, selected properties that you can access by running these two functions. You can also get all the available properties by simply running this loop. By running this loop, you will get all the list, all the available properties there. So so this is for the function get device properties. You can get additional properties by from this get attribute function. So in the same way, the function accepts as an argument this class, which in its turn has some attribute here that you can define. And so here I selected a couple of attributes that we want to get their values. We have here we want to know the max threads in a block in X direction, in Y direction, in Z direction. We want to know the size of a warp. Even we want to know the maximum number of threads per block. So by running this script, you get an output here. You can get, you can see that the max threads per in each direction is 1024. We have 64. That's the size of the warp, and the maximum threads per block is 1024. Means that you can set a configuration such that the max thread that you per block should be 1024. So you can play around with this number such that the total should be 1024, the size of the block. So and you can get additional attributes. You can access additional attributes from this link. Next, let's talk shortly about the memory management. It means how you can allocate GPU memory from Python, how you can free the memory, and how you can copy a simple example between the host and the device. This is a general syntax, how you can allocate GPU memory, how you can copy data between CPU and the GPU, and how you can free the memory. To allocate a GPU memory, you simply use this the function heap imalloc. It accepts as an argument the size in byte and of the vector, and this is the pointer to it points to the memory to be allocated on the GPU. So to copy data from the CPU to the GPU, this is a very direct, simple way of copying data. But there are other optimized way of copying data that I'm not going to address them here. So with the function heap memory copy, so you have here as argument destination. This is the destination where the data will be copied to. So it can be a host or it can be a device. If it's a device, it's a pointer. If it's a host, it's an NumPy array. So you have the source from where the data will be copied, either from the host of them or from the device. And then you have the size of the vector of the data. This tells you about the direction of copying the data. It goes either from the host to the device or from the device to the host. So this argument, it specifies the direction of copying the data. So once the data is on the GPU, after doing some computation on the GPU, you want to free the GPU, and simply is done by heap free. So this is some basic function that you can use to do some GPU memory. This is an example, example number 2, that you can run and get an idea about how to implement these functions. The example here, after importing this module, we take a simple example where we generate a random array stored in 1D dimension with a single precision. So we allocate the device pointer with the size in byte. This is a single precision. So then we pass the device to the memory copy to copy data from the host, meaning that we want to copy the host data and to the GPU, which be stored on device data. And then you have the size of the data, and this is the direction. So in this case, we want to copy from the host to the device. So now that the data is located on the device, probably we want to do some operation, and then we want to copy back the data. So in the same way, with the same function, but here the direction is from the device to host. And after, you can free the device. So this is an example that you can run, and you can check if the data stored in host data /bash is the same as the data stored in the host data. Okay. The next, I will tell you a little bit about how you can call a math library from Python. A very simple example about heap, a function within heap plus. So this is basically the libraries, heap libraries that can be called from Python with heap Python. So what we will be focused on, I will focus on this library. So let's, yeah, this is the subject of example 3. Generally speaking, the way you can call a math heap library from Python is in 3 steps. The first step is you need to initiate the library, and then you need to call a function within that heap library, for instance, in this case, heap plus, to do the computation. Once you've done the computation on the GPU, the next step you need to destroy the library handle. The example that I'm showing here, and I'm showing in the example 3, is the function heap plus. This is a function within heap plus that basically computes the absolute value of the element in a vector with a single precision. This is the syntax how you can call this kind of libraries. You initiate the library by creating a heap plus create, then that's stored in the handle. So a handle basically contains configuration and setting information about the library. Then you call heap plus function, and that's what the computation, it does the computation in the GPU. So it accepts as an argument handle and the number of elements of the vector, which is here, x is a pointer. Then you have this increment. This increment is basically, it is the, if increment is 1, it means it will take all the elements. If the increment is 2, it means that it will take every second element within the vector, and the results are stored in this pointer. So after running, you need to destroy the handle simply. So I think I have passed 15 minutes. What I suggest now is probably we will not have time to go through how to compile and create kernels. What I suggest now is you can take a little bit of time, the break time, and try to run an example. And I will be here around until 2:30, so we can we can talk about something different. Okay, we can do it like that.
Yes. Yeah, during the trial run, if you come to some problem, you can also leave your problems at the Hagen document, and Haitram will reply to you later. emulator.
Yes.
Yeah.
Yeah, during the time.
Yeah. I think let's take a coffee break until 30. I mean, we take a break for 30 minutes. 1-3.
Yeah, let me. This is the hands-on examples. Yeah, I forgot.
You can just leave this web page right here.
So anyway, I will be here, and in the case you have any issues in running the examples, and we can discuss them more. Okay. Okay, I see that some of you couldn't activate the environment. I will try to share a terminal, and we can try to do it together. So we'll first create an interactive session. I will load the module. So then source in the environment. So yes, the environment is sourced. Yeah, next. So I can run the example device prop, the first example. Yes.
Oh.
So you can see here, I'm not really, you can see here the information, the properties that we want to print out. And so I'm not really sure. I'm not really sure why heap not found. Of course, the alternative here is that you can install heap yourself, and you can follow. There is a setup on a README file. So you should be able to install heap Python and NumPy, because this is the two packages that we need, that basically we need. So these are the packages. I will copy paste that on the chat. Yeah. So of course the first thing is to create an interactive session. Hopefully it works. Just let me know if it doesn't work. Then we can try to have a one-to-one discussion about it. Good. So we'll move a little bit to try to do something different. So the idea behind this presentation is to do some multiple GPU programming. So then you have the ability to run on many GPUs, and not only within a single server, but across multiple nodes. So this is very important, because we have here probably 1.5 hours. So the main goal really here is really to trigger your interest to programming with the use of MPI library. That's really the most important thing. And in 1.5 hours, I don't think we will be able to talk about MPI. I will try to provide an overview that would help understanding MPI for those who are not familiar. And the main motivation here is that you have seen OpenACC and OpenMP. So this is basically limited to a single GPU. You could obviously use asynchronous OpenACC to run on multiple GPUs, but once again, you will be limited to a single compute node. So therefore, there is a need for some applications to run on multiple GPUs, not only within a node, but also across multiple nodes. And this is the case for some large application that probably wouldn't fit in a single memory. And then Therefore, there is a need of running the application in the distributed memory. And also, more importantly, is that they are available as exascale supercomputers such as LUMI. I think this is really a good opportunity for a researcher to take advantage of the capacity of this kind of supercomputer to do some interesting science, I would say. So that's basically the motivation about why multiple GPU. And obviously, not all the applications would need to implement multiple GPU programming. So if there is a need, probably for large application, the general scenario that I will be presenting is we consider a distributed system that consists of multiple nodes or multiple servers. That's the case for a cluster or a supercomputer, and such that on each node you have some CPUs and you have GPUs. And the idea is how to implement multiple GPU to be able to utilize the whole capacity of a system. So in this presentation, I will be using MPI library to communicate between different compute nodes. And we use some directive model that you have seen yesterday to communicate between CPU and GPU to offload copy data between the CPU and the GPU. And then the distribution should be done with an MPI library. This is the scenario that I will be presenting today. And I will cover two main concepts. There's a traditional concept that run MPI in the host, because originally MPI is developed to run on the CPU. And there is another interesting concept that is well optimized, and we will see that it provides a significant improvement when it's implemented. And the implementation is really very simple, as we will see. We will see some examples. As I said, I will be focused on two main concepts: the traditional MPI, where the MPI library is not aware of the existence of a GPU. So this means that the MPI runs on, it involves the CPU memory during MPI operations. And there's another concept, as I mentioned, it's referred to as GPU-aware MPI. So this is an interesting concept that it doesn't involve the CPU memory. And we will see some examples covering these two concepts. So we will have some example. The example in terms of MPI will be focused on point-to-point communication, mostly sending some MPI, some data between a pair of processes. And there will be some hands-on example and exercise at the end. So there will be here three parts of this. First, I will try to have 15 minutes on each part, such that we can have 10 minutes of examples on each part. So the first part, I will focus on how to assign each MPI rank to a specific GPU. So that's the first part. And then I will stop, and then we will have an example that you can run. So the second part will be about how combining MPI with OpenACC or OpenMP. And this is the traditional concept. So, and we will have another example there. And last, we will have the concept of GPU-aware MPI. And this is basically the function, the MPI function, and the directive that I will be using for the examples. So that's basically the main outline of this of the presentation. So first, for those who are not familiar with MPI, what is MPI? I would say simply MPI is, you can think about it as a framework that has a collection of libraries and interfaces. So it allows to communicate between different processes that are distributed in a system, so such that different processes, they can communicate within each other, either via message, either in a point-to-point communication, which means that the process one will send a message to the process two, and the process will receive that message, and they will exchange data via a point-to-point communication, or a collective communication, which involves a group of processes where you can broadcast data across multiple processes, or gathering data, or even reduction of data. So, so as I said, this is the scenario that I'm going to present, and we will use MPI to communicate between different different nodes. But the first question here is, when GPU and CPU are involved, it's very important to ensure that each process on a CPU is assigned to a specific GPU. You don't want to get in a situation where the same process on a CPU use or when you have two processes on the CPU are running on the same to the same GPU, because there is a potential crash of the application. And the reason behind that is that GPUs initially are designed to handle multiple threads, task-based, not multiple processes. So running two processes or on the same GPU you can run out of memory, and the possibility of running GPU to GPU communication will be might crash. So that's why it's very important to ensure that each MPI rank is assigned to a specific GPU. So the way we can do that, one of the way to do that is let's first, because there is a key element here, which is the global communicator. So global communicator here, you can think about it as an umbrella of multiple processes that run on the CPU. And the example here is we have two nodes here. So each node here contains 4 CPU core. So we can think about it as the global communicator. It consists of 8 processes, because we have 4 here and 4 processes here. So each process can run on a single CPU core. Another important here, because I have mentioned the MPI rank. So here each process has a specific ID that make a difference to differentiate between 2 processes. So each process has an ID that we call MPI rank. So the idea here behind assigning each MPI rank, which is MPI rank is an ID of each process that run on a CPU, is the first is to split the communicator. Instead of having a global communicator that contain 8 processes, we can split the communicator such that each subcommunicator contains processes that run on the same compute node. We have 2 compute nodes here. So we have 4 processes here, and that can be assigned to 4 GPUs, and the same on the compute node, meaning that here we create a subcommunicator. Instead of having a global communicator with 8 processes, we have a subcommunicator that contains only 4 processes. So in this way, we ensure that each process will talk to a GPU within the same compute node. And then we will avoid situations where multiple processes can use the same GPU. So that's a concept in somehow. So now, how to implement that in an application? There is an MPI function called MPI common split type. So this function, what it does, it accepts as argument the global communicator. And then it split the communicator to subcommunicators. The output of this function is host common, and this is a subcommunicator. The subcommunicator contains, as I mentioned, processes that run on the same compute node. And even more important is that this function accepts this argument, which enables to create to have a shared memory of these processes. So the subcommunicator here is passed as an argument to another MPI function, and the output of this function is the host rank. This is, I mentioned it, this is the ID of each process within a subcommunicator. Means that for the process 0, it has an ID, a unique ID. For the process 1, it has another ID. And this is very important as I mentioned, to ensure that we don't want multiple processes to run on the same GPUs. So this is the picture on the MPI side. We split the communicator, so now we know that each subcommunicator has some processes that run on the same compute node. So the next step on the GPU side is there is an API function in OpenACC that accepts as an argument the host rank, which is the output from the MPI. So this is the ID. The ID of each process is passed as an ID to each GPU. And this is the way we ensure that each process will will be connected to, or will copy data to a specific GPU. So we won't get in a situation where multiple processes will run on the same GPU. And we have this additional function that tells you how many GPUs are available within the same compute node. So this is basically the syntax of how to assign each MPI rank to a GPU device. This is the picture on when you combine MPI with OpenACC. Yeah, this is a summary. So on OpenMP, on MPI OpenMP, you can see that it's the same structure. The syntax is slightly different. So here you have ACC set device number, but here you have the default device. And the same way you can, with OpenMP also, you can get the number of GPUs available on a compute node. So that's this is really the syntax, as I mentioned, how to assign each MPI rank to a GPU device. So what I suggest now is there's an example one, where it runs where it contains an example of how to assign each MPI rank to a GPU device. So I suggest that you spend probably 10 minutes, and if there is need of time, so we can add another extra 5 minutes. Okay, and if there are any issues, let me know and we can go through it. Okay, I give you 10 minutes and we are back in 2:50, yeah, 55. Yeah. Okay, I hope you were able to run the example one. So the example basically will display different MPI ranks and the associated ID of GPUs. So that's the main purpose of that example. Okay, so I think we move now to the second part. This is the traditional MPI where the MPI library is not cannot interact directly with the GPU. I will present two aspects here on the CPU and on the GPU. The example that we take here is we consider a 1D array where we have where data are stored, and we partition the data into different segments, such that each segment will have will run on by a process on a CPU core. So each part has an ID, a different MPI rank. So the first part, for instance, has the rank 0, the second part rank 1, and so on and so forth. So the MPI library will take care of sending all the data across different CPU core. Now on the GPU, what happens is that we will use a directive model, for instance, on OpenACC, to copy data which are already located on different CPU core, and will be uploaded to a specific GPU, knowing that we have already assigned each MPI rank to a specific GPU. The problem with this traditional MPI is that once you offload the data to the GPU and you are doing some computation on the GPU, and you need to run MPI, you have to go back to the CPU and then run different MPI functions. And this can be done iteratively, meaning that you need to copy the data to the GPU, do computation on the GPU, and then go back to the CPU, where MPI can do some MPI operation, like sending, receiving, or gathering data, or whatever. So this is actually is a bottleneck in data in transferring data between the CPU and the GPU, and it will cost a lot of time in terms of communication. So that's why there is another alternative, of course, that we will see in the second example. But before that, I want to show an example where we use traditional MPI. So MPI on the CPU to distribute the task across multiple processes, uploading the data to the GPU and do some computation in the GPU, and then copy data back to the CPU, where MPI can do some operation on the CPU. So the example that I will be showing, it involves MPI send and MPI receive. And we will use some directive. Probably you have seen this directive on this morning. I will show you an example how these two functions, how MPI functions can be combined with OpenACC directives. First, on the CPU side, this is an example which shows only MPI. In this example, for simplicity, I will take only two MPI processes. So our data are split in two portions. So each will run on a different process. So the syntax here is that what I want to do here, I want to communicate the data that are ranked 0 to the neighboring process that have the ID 1. I want to do that in an iterative way, and then I want to measure the time it takes to do this communication. So this is basically the MPI part. So we will send the data located in this pointer. The rank 0 will send the data to the rank 1, and the rank 1 here will receive the data from rank 0. Rank 1 will receive data from rank 0, and it will send the data back to the rank 0, and the rank 0 will receive them. So this is a communication process that will happen between a pair of processes. We will see an example where you can see the relevance of this example. So we have this MPI functions, and we want to combine it with the OpenACC. So this is the syntax how we combine it. For simplification, I considered here just two calls to simplify the problem. And the way to implement OpenACC on the top of it, we first consider a data region. This data region is determined by this directive: enter data and exit data. So we have some vectors here. So what we do here, basically, where the compiler encounters this syntax, what it happens is it will generate a code that will run, that will copy data to the CPU, to the GPU. So once the data are ready on the GPU with the use of this copy in, so this class copy in, what it does, it allocates memory on the GPU, and then it copies the data to the GPU. So our data are here in the GPU. So we can do some computation here. Once we are done, we want to go back to the CPU. And going back to the CPU, this is done by this directive update the host. So this is the traditional way of doing MPI. You go to the CPU and then you run some MPI operation. In our case, we took the example of sending and receiving data between two processes. So once you are done with the MPI operation here, you can go back again to the GPU. But interesting to note here that once you are running thing on the CPU, the GPUs, they are idle. This is not a good thing. Anyway, so we copy the data to the GPU, and this is done by this directive. So now, once again, you are on the GPU where you want to do some computation. So when the computation done, and you encounter, and the compiler encounter this function, what happens is that the data will be copied back to the CPU, and then everything is deleted from the GPU. So this happens in an iterative way. You copy data from the CPU to the GPU, you do computation on the GPU, you copy data back to the CPU, where you apply MPI function to do some communication on the CPU level, and you iterate that over and over again. So, and this is basically, in general, it doesn't lead to a good performance. And the example number 2 will show that the bandwidth during the communication is really low. Before that, I show you another picture where we compare MPI OpenACC on this side and MPI OpenMP on that side. What you can see here is that the structure is the same. The syntax is slightly different, meaning that if you have an OpenACC code, you can still port it in a straightforward way from OpenACC to OpenMP. Yes. So this is basically, these slides illustrate the concept of traditional MPI when it's combined with either OpenACC or OpenMP. To show you the bottleneck of using this concept, I have an example here, the example number 2. You can choose either MPI ACC or MPI OpenMP. So what this example it does, it simply first it distributes the data across multiple processes, and then it will send and receive data in the same way as I have shown you just a minute ago. Is simply there is the example, there's no computation. We have simply communication. We want to measure the time it takes to communicate between a pair of processes. That's really the purpose of this example. We are going to send different size of data between the 2 processes. We will limit here to only 2 processes, and then we will send and receive data and see how long it takes, and then we will compare that with another concept. So, whereas I suggest that you take probably 15 minutes to run this example. You get an output. And we come back here and we will discuss the low value or the high value of time it takes, the long time it takes to communicate between 2 processes. Okay, so yeah, I have some output here. I would like to see your output, and we come back in 15 minutes to talk more about. Okay, so anyway, I will be here around if you are encountering any issue with running the example. Okay, so I hope you managed to run the example. I have already seen there's output on HackMMD. So this is my output. And okay, what you see here on the left side, this is the time it takes to transfer 128 bytes of data, and so here you have the timing, and you have the size of the data, and here you have the bandwidth. So the bandwidth basically it measures the speed across a network. So it's simply the size of the data divided by the time it takes to communicate that size of data. And to make sense of the numbers here, because for 1 giga, transferring 1 gigabyte of data, it's the speed of transferring 1 giga of data is about 6 gigabyte per second. So this is basically slow. So why is it slow? To understand the numbers, so let's look at first the numbers of networks. This number they are taken from the LUMI documentation. So what we have here, we have a CPU, and the CPU, the speed at which the CPU can access the GPU memory is 205 giga per second. The speed at which you can communicate between the CPU and the GPU is about 72 gigabyte per second bidirectional. This is a bidirectional bandwidth. So you have 36 on one direction and another 36 on the opposite direction. And then you have the GPU, the speed at which the GPU can access the GPU memory is about 1.6 terabyte per second. This is very fast. And between two GPUs, you have 400 gigabyte per second in two directions. So you have 200 on from GPU 0 to GPU 1, and another 200 on the opposite direction. So this number, this 400, this is very specific to MI 250, because on MI 250 you have two GCD, or two separated GPUs that are sitting on the same die. And you have the network between the GPU and the network interface card. This is 50 gigabyte per second on two directions. And you get here the storage. You can see that reading and writing is very slow. So given this number, you can see that 5 giga is really slow. So the reason behind that is, we can explain from this, you can understand this from this picture. So what happens in this traditional way of implementing API with OpenACC is that initially we assume that the data are located on the GPU memory, because we copy data to the GPU memory. So what happened is that the GPU, you need to run some API to access the data from the GPU and then transfer the data to the CPU. So then from the CPU, you need the CPU to also, because you have 1 giga of data, wouldn't fit in the shared memory. So it needs to be accessed from the main memory. That's another extra path. And then it needs to go back again from the CPU to the GPU. You can see that this is a very long path in order to do some communication between two processes. And this long path that you can see, that explains really the low performance in communication. So it's very important to note here that there is no computation. There's only communication. That's what we measure. And that's basically traditional way. But what we want actually in terms of optimizing this presentation is, we would like that the data can be transformed this GPU directly to the GPU. We don't want to go through all this path and go back and forth. So that's the basic idea behind the GPU aware MPI that I'm going to present. Going to present in this section. So what is GPU aware MPI? So basically, this is a concept in which MPI library can directly talk or can directly interact with the GPU memory without the need of passing by the CPU memory. It directly interact with the GPU memory, and the way it does that is very simple. It's the device pointer that point to the memory, to the GPU memory. That device pointer can be passed as an argument to an MPI function. That's it. That's really the main idea behind it. And the interesting aspect of this concept is, it happens not only within a single node, but also it does the optimization also across multiple nodes. And here it takes advantage of the GPU direct technology that has been developed by NVIDIA. So that's shortly what is GPU aware MPI. To understand it much better, let's go back to the traditional MPI without GPU awareness. So this is a picture that we have seen. So you have to do MPI operation with the CPU, copy data to the GPU, do computation on the GPU, copy back to the CPU, do MPI operation. In GPU aware MPI, you really don't need to go back to the CPU. You don't need to go back to the CPU. So the MPI library can directly access the GPU memory. You don't need to go back to the CPU, and that is really the key in this concept, is the MPI library can directly access the GPU. And the way to understand it, this is one of the way to understand this concept. And there is a feature that NVIDIA has developed in unified virtual addressing. You can think about it as all the GPU memory here is combined as a single virtual memory address. It's a single virtual memory address where the pointer of each GPU can access that memory address. What it means to have a single virtual memory address for all the GPUs, it means that the GPUs is the GPU 0, for instance, and the GPU 1, they can really directly talk to each other without going back to the CPU. And that's really the key element in this GPU aware MPI. And because of that, the device pointer can pass directly to an MPI library. So the MPI library here, it automatically detects the device pointer, and then it will do the right thing. So the key element here is really you need an MPI library that support a GPU programming model, and the last version all they support this feature. And because of these features, you can make two GPUs to talk to each other. So this is the picture on a single node. On the multiple nodes, the same concept holds. Before we talk about it, I want to show you first how it works in multiple nodes in a traditional way. In a traditional way, once again, you have the data on the GPU memory. So the GPU you need to access the GPU memory from the GPU, copy the data to the CPU, and then again to the CPU memory, and then go through the network interface card. And from here, you go to another network interface card or another node. Once again, you go to the CPU, you copy. It's a very long path. That's traditional way on a multiple node. In GPU-aware MPI, it takes advantage of this GPU remote direct memory access. And the data is directly transferred from the GPU memory directly to the network interface card. You don't need to involve the GPU to make any transfer of the data nor the CPU. So it goes directly from the GPU memory to the network interface card. And this basically is handled by the GPU driver. So you don't need basically to care about this about it. So at this staging point, the data will be transferred to the network interface card to another compute node, and from there it goes directly to the GPU. And the example that we will run in a moment, it will show you really how fast implementing this concept. Let's look at first an example here, how you can implement it in an application. So we have seen this picture, that's the MPI side. So that's the GPU over MPI with OpenACC. You can see if you have an application that you have already MPI, you simply define, as I mentioned previously, a data region where you can include the directives to copy data from the CPU to the GPU. We are on the GPU do some computation, and then that's the important feature in OpenACC. You use this directive. This directive accepts this argument as a pointer. So this device pointer, as you can see, are passed to the MPI function, and by passing that, so the MPI will do what is necessary to communicate between two GPUs instead of communicating between two MPI process on the CPU. So that's really, as you say, it's really simple. You have an MPI piece of code here. You simply define or specify a data region, and you simply add this directive where it includes the pointer, and those pointers, they will be passed to the MPI function, and the communication will be done. So this concept I'm showing the example here in OpenACC. You can do the same with CUDA. It's the same thing. You simply pass the pointer, the device pointer during the copy memory with CUDA, and you can pass it to the MPI function. So you can see that this is the implementation is really simple. But of course, building the MPI in order to enable this feature, that's something you don't need really to care about, because administrator of HPC system, they handle that operation. Yes, that's an important thing. You basically need to enable GPU aware MPI, and this is by simply running this by specifying this the environment variable. And the environment variable is very specific to which MPI library you are running. On Lumi, we have create MPI, so that's the syntax. For OpenMP, for OpenMPI, there's another syntax that is a bit different, but the concept is the same. So, so this is a comparison between our GPU aware MPI with OpenACC and GPU aware with OpenMP. Once again, you can see that the structure is really the same. There is a slight difference in terms of structure. So once again, if you have MPI OpenACC, you can straightforwardly port it to MPI with OpenMP. And this would be necessary if you have OpenACC with C or C++, because this is not supported on Lumi. So in this case, you need to port it to OpenMP. Okay, to finish this part, I have an exercise here, an example that you can run is similar to example 2. So once again, it measures the time it takes to transfer the data between two during the MPI communication. So we will be surprised about the time it takes by just enabling this feature. And we come back and we try to discuss the result and why, and what is the main difference in those results. Okay, so I suggest that you take probably 10 minutes, and we come back for another 5 minutes to discuss the results. And if you have any questions, that just mention them on the Hack community, and I will look at them. Okay, so I see you in 10 minutes. Okay, so I hope you are able to run the example. I have some output here. This is the example I ran. I think about during the last week or this weekend. So I see some slight difference between the result posted on HackMMT. On the left side, you have the traditional MPI compiled with OpenACC, and on the right side, you have the GPU aware MPI. One thing that you will notice here is that if you are operating with small size of data, you basically wouldn't see any a big difference. So, and that is trivial because the network is really fast, and slow data wouldn't impact the computing. But if you look at for transferring 1 giga of data, so you can see that on traditional way you get almost 6 giga speed of 6 gigabyte per second, while for the GPU MPI you get up to 80 gigabyte per second. So this is really a significant improvement here. This is a factor of almost 13, and that's by simply changing a few lines in the code. You get really a huge improvement. And another thing that we didn't have time to run another example is you could try to run it on 2 nodes. This example runs on a single node. You can also get the taste of the networks between 2 nodes, the slingshot, and you can change the script having 2 nodes, one GPU in each node, and then you can run the same comparison to get an idea about the difference between these two concepts. So I think we are just in time. I have a few minutes to conclude. So that's basically the explanation of the difference between these two concepts. I have mentioned that for the traditional MPI, you have a very long path for load by the data to be able to communicate between processes, while here in the GPU-aware MPI, there's no involvement of the CPU, there's no involvement of the CPU memory, and there's even no involvement of the GPU itself. So it's a direct GPU memory to the GPU memory. This is a very interesting concept. This is, I want to mention here that it's possible also to get some extra optimization to do some binding of each MPI rank to the for each CPU core to the closest GPU. The reason behind that, once again, is because of the network, and you can see it here in this architecture. What you see that if this is you have 4 NUMA nodes here. If this CPU core is going to talk with the GPU number 7, you will get some you wouldn't get that speed compared if the GPU 5, for instance, is talking to the GPU, which GPU is this? To the GPU 4, because here between GPU 5 and the GPU 4, the interconnect is about 400 gigabyte per second, while the communication between GPU 5 and the GPU 7, it's 100 gigabyte per second. So this is very important to me, that what you want that this CPU core to communicate with this one, and the CPU core number 7 to talk with the GPU 5. Then by implementing the GPU-aware MPI, you will get these two GPUs talking to each other with a high speed instead of GPU 5 talking to the GPU 7. And the way to do that in this is, you simply when launching the application, you specify the binding option here, where you specify which CPU, the number of CPU cores. So you can get this number by running, for instance, it's run LCPU when you get to the compute node, and then you can select the CPU cores. Note that the first CPU cores on each NUMA node, they are reserved for some technical purposes, so meaning that you shouldn't choose the CPU core number 0, 16, 32, 48. You can choose just the second number of CPU core. So this is one of the ways to get an extra optimization. Once again, you will notice the improvement here where you have a large set of data. To conclude very shortly, I have shown you two different concepts. These are traditional concepts where its implementation, it is to really large high latency, it's large communication time. And there's another concept, very simple in terms of implementation, and it takes advantage of the high speed of network. And by implementing this concept, you can see that you can get a significant improvement in terms of communication. And the most important thing here is that the concept is the same whether you implement that on CUDA or HIP or OpenACC. The concept is really the same. The syntax, of course, is different from OpenACC to CUDA to HIP. And the most important thing here is that the simplicity of this concept in terms of implementation. And we have seen, if you have an MPI code, so you simply have to specify a data region where you can implement either an OpenACC, or you can even do CUDA or HIP. So that's what I have for this presentation. And if you want to challenge yourself, I have some benchmark here that we ran for 2D Laplace equation. We ran from 1 GPU up to 8 GPUs. I compare here the traditional MPI with GPU and the GPU-aware MPI. We see that there is a factor of 10 roughly between 8 and 10 improvement for this is a benchmark for solving Laplace equation into D. If you are interested, you can. There is an exercise. It's about solving Laplace equation in 2 dimension, and you can, if you want to challenge yourself, you can implement the models that we have seen either with OpenACC or OpenMP, and see, and you can compare your implementation with the implementation that I have in another folder solution. There is a solution there, so you can run the exercise, you can implement the model, and you can compare with the result stored in the solution. So I think that's what I have. I think we are just in time, so I stop here and.
Super good.
Can you maybe show again the spinning, how you exactly know which core is binded to the GPUs? Explain this. Yeah, the next one.
This one.
Yeah, where you now have this 4957. Where do you get this exactly from?
Yeah, you can get it either from here. So you can because you have NUMA node, NUMA node 0. So you can see it here. NUMA node 0 consists of you have 8 CPU core here and 8 CPU core here. So mean that from the NUMA 0 you have to pick up one CPU core from 1 to 15. Okay, it's very important to mention here that there are multiple threads in here, mean that you have double threads on each CPU core. Anyway, you can pick up a number from 0 to 15. That's one CPU core. Another number from 64 to 79. Let me see. Yes, from here. So you can pick up either one, the CPU core number 1, and the CPU core number 2, number 9. And those two will automatically bind to GPU 5 and the GPU 4. By specifying 1 and 2. And on NUMA node 1, you have 17, for instance, and 25, or 18, 26, and this automatically will be bind to GPU 2 and GPU 3. So the same. So one of the way you can do it, you can access the architecture of the compute node on LumiDoc, and you will see the numbers there. And another way is, I mean, if you accessing the Lumi, the compute node, and you print out the LC CPU, and you can pick up the numbers. Another important thing here is that if you want to run on less than 8 GPUs, you need to add exclusive directive on your SLARM. Otherwise, it wouldn't work. Mean that you have to allocate the whole compute node. It will cost you extra. You have to pay more. That's the downside of it. But if you have 8 GPUs, I think it's really a good option to bind this binding. It's a good option.
You just can take any number between 0 and 15.
Yes.
Although you said the lowest number you shouldn't use because there is some special whatever.
Yeah, those first number 0, 0, 0, 8, 16, those they are used for some specific purposes. So mean that if you specify 0, your job will crash. So you have to use this. Another thing also.
Just use the next one. Or,
the next one. One. That's
okay. Yeah, thanks much. A bit clearer now.
Yeah, thanks.
Yes, thank you, Adam. And I will upload this update this content at our lesson materials.